Okay, so welcome to this course on error correcting. So this is basically an elective course for most of you. Some of you may be just sitting through the course, which is fine. So just maybe a show of hands. How many of you are BTech students? The rest of you are masters and PhD. How many of you have taken a course on digital communication and or information? Okay, you're taking this. Has anyone not done a course in linear algebra or and probability? Okay. But have you done some undergraduate course on probability? What is the level of linear algebra or probability that you have studied?
Competitive than like 80.
Okay, fine. So you've not seen abstract vector spaces or anything of that sort?
Not that detailed.
Okay. Okay, so we have a course web page. I think if you've registered for the course, then you will certainly get the link to Google Classroom and the web page. If you have not formally registered for the course, then just send me an email and I will add you to Google Classroom. So this course web page is available from my homepage as well. You can go to teaching and then from there you can get to this. All right, so the basic background that I expect is you should know some linear algebra and matrices and should be comfortable with probability. You should have, it's preferable to have done a course on information theory and digital communication, although it is not mandatory at all. The motivation will be more clear if you've taken a course on these two, but otherwise I will not assume any sort of prerequisites whatsoever. For the second half of the course, I will assume some information theory background. For example, you've seen channel capacity before, but apart from that, nothing else. And of course, you should be comfortable with programming in one of these languages, C or C++ or Python. Okay. This assessment part is still tentative. Things will change in the first couple of weeks depending on how many people are there and interest and so on. But basically, there'll be at least one midterm exam. There'll be around 3 assignments or so, or maybe more. And in the end, we'll have either a final exam or a paper project presentation, something like that. I mean, this will anyway evolve as we go along. So anyway, all of this will be updated on this page. So the class is in slot P here. Does anyone have issues with the slot? So I assume that P slot works for everyone. Okay. All right. So I won't follow any single textbook for this course. Even the topics are kind of tentative. There are some topics that I really want to cover, but beyond that, it is up to, we'll see how things go. If there's any specific topic that you would like me to cover, then please let me know. This is an elective course, so we have some flexibility in choosing what we want to cover and what we don't want to cover. But as far as I see, most of you are EE students, with one exception, CS. And so it's mostly EE and CS background, which is good. So in fact, we'll cover this course and you'll see kind of different flavors to error correcting codes. So in the beginning, we'll see more of a combinatorial CS type flavor. And towards the second half, we'll jump into exactly what is implemented in practice and in communication systems in particular. So I'll mention which reference I'm following for each of these topics. Some topics I will not follow any particular reference, but certainly for most part of at least the first half of the course, these two references are what we will follow. Essential Coding Theory by Venkateshan Guruswamy, Atri Rudra and Madhusudan. So this is available online for free. And the other book that I'll follow to some extent is Introduction to Coding Theory by Ron Roth. So More or less, just this reference would be enough. So we'll cover the content mostly here, but just for I'll probably follow the presentation and style of the book by Ron Roth to some extent. The second half, there is no single reference. I'll cover what are called LDPC codes. And here there'll be a couple of papers that we will discuss, and also one book, Modern Coding Theory. This is a huge book on devoted exclusively to LDPC code, so it covers far more than we can ever hope to do so. We'll probably just go through first. We won't be able to go through maybe 2 chapters of this book. There's a lot more, and there have been several developments since the book was published. So again, I will not have time to cover everything, but here, I mean, there are also some links for further reading of different applications of coding theory and some of the recent developments. It's not an exhaustive list, but if you're interested to know more, you can just go through these references. All right. So again, we have a tentative schedule, but this is this may vary a bit. There are certain things that I definitely want to cover, but some topics we might change here and there. So at least at the end of this course, I would expect you to, I want you to be familiar with some basic codes which are implemented in practice, the basic principles behind error correcting codes. How do you construct an error correcting code? How do you encode a code? How do you decode certain codes? And also implement some of these. So there's a mathematical aspect to it in showing that these codes are good in some sense. But there's also the problem of how do you efficiently encode, how do you design codes, how do you decode codes, so how do you construct these algorithms and so on. And hopefully by the end of this course, you will see at least one code which is actually implemented in practice, and you will also implement one of them just using a tiny simulation. So this course, this topic of error correcting codes is very old. It started way back in the 1950s and 60s. But then there was a resurgence in the 90s and early 2000s, because up till then it was mostly a theoretical problem. Right? It had a very nice mathematical flavor, but a lot of it couldn't be implemented. So the major development in algorithms in error correcting codes came only in the 90s and 2000s. And that is in fact what led to the cellular revolution. So it is because of these error correcting codes that we're able to reliably talk to each other over long distances over cellular phones. Because otherwise, wireless communication channels in particular are extremely noisy. And without any digitization, without error correcting codes, it's in fact impossible to reliably communicate with the kind of form factor for phones that we have today. Okay, so before we get into the technical content, any questions regarding the logistics? So, any particular motivations for taking this course? So, do you plan to use this in your research or project or something else? We have a small class, so I expect this to be as interactive as possible.
For a project,
Okay.
turbo codes were implemented.
Okay, so turbo codes. I originally did not plan to cover much of turbo codes, but maybe I can add that, maybe a class or so of turbo codes. Any other motivations? Because this will also help me to choose what topics I want to cover. If there are any specific things that are of interest to you and you think you would be that would be helpful to you, I can at least add in a little bit of that. Anyone else?
This would add in my research, but I just want to know, like, from one side, you are sending something to the other side in between. So we are using some channel. will be perfect. And so all these codes are designed to what extent we can correct or something happens.
I mean, there are a lot of connections between error correcting codes and many other problems in theoretical computer science. We won't really go through those connections, but at least we'll see some examples in this class about applications of error correcting codes in various different.
Took source coding and channel coding last semester, so
That's good. So in a sense, this is a complementary to what you saw in the channel coding course. So in channel coding, we only talked about what are the fundamental limits for communication over a channel. And here, the main goal is to understand, to some extent, we'll also see some other kinds of fundamental limits, but also how do you achieve those fundamental limits? How do you design algorithms? How do you design efficient algorithms for communication? Okay, so let's get started. So the most typical example for where error correcting codes are used are in all digital communication systems. Any sort of cell phones, Wi-Fi, even optical communication, all of these employ error correcting codes in some form. So if you look at a typical block diagram of a digital communication system, then this is what it would look like. There's typically a source, right? So the source could be either your voice signal, or it could be some data that you want to transmit over the internet, or it could be an image or an audio file, anything of that sort. So this source could be, it should be a continuous time waveform, for example, your voice, but it could also be a sequence of bits, like you have an image that you want to transmit or some data packets that you want to send across the internet. So for us, that's a black box, it's a source. Right? And this needs to be processed in some form. It's typically digitized if it is not already digital. So there's an analog to digital converter. There is some quantization happening. So that's what we broadly call source coding. So if you've taken the course on source coding, you've seen a little bit of this. So it's typically you convert it to digital and you also compress it so that you're communicating as efficiently as possible. And once you do that, after all, you're communicating over a noisy channel. So you use some kind of an algorithm, which we call a channel encoder, to convert this to sort of add some kind of redundancy. We'll see what we mean by redundancy and so on. But you add some kind of redundancy so that eventually you'll be able to recover the message that you had. Right. So the sources could be a continuous time signal of t, or it could be a discrete, it could be an image, or some kind of data, could be anything, right? And what does the source encoder do? It processes this so that ultimately you have a sequence of bits. So let's assume that this is converted to a sequence of k message bits. This is what we call the message. The input to the channel encoder will generally be called the message. And the goal of channel coding is to ensure that the message is recovered at the receiver as reliably as possible. Again, I'm being very loose with all of my statements here. We will see more of this as we go along. So essentially, what the channel encoder sees is a sequence of k bits. And that is going to be our fundamental assumption throughout this course. So we have a sequence of k bits that we want to reliably communicate across a noisy medium. That is the goal. Right, so you add some kind of redundancy and convert this into maybe an n-bit sequence, or it could be some n symbols over some alphabet. We'll make this more formal, and that is fed to a modulator. After all, now we have digitized everything, but ultimately we are communicating across a continuous time channel or some continuous time medium. You can't transmit discrete packets, right? So this is typically whatever modulated using sines and cosines. There's some frequency translation happening, whatever you use the favorite modulation scheme of your choice, and then send it across the medium. So this medium could be It could be an optical fiber. It could be free space. It could be wireless channel. Could be a wired channel, some coaxial cable. Again, it's immaterial. So this is really where this is really the part of the communication system which is the most unreliable. Right? That's our assumption. So we're assuming that all of these blocks are extremely reliable. They work as we want them to, and the only source of noise or corruption is being introduced by this block that we call the channel. And then once you have the channel, once you transmit across the channel, the receiver is going to get something, and then this signal is demodulated to give another sequence of n symbols or n bits. Right? So this could be an erroneous version of this Cn. Right, so it's not exactly as Cn. The goal is to somehow recover this Mk from Yn. So that's why we use this whole business of channel decoding to get some estimate of the message. And then this is again, if you had a voice signal, now you have a sequence of bits. You have to convert this into a continuous time signal. So you could have a digital to analog converter. If you had originally compressed the original source, then you have to decompress it and so on. So these are the basic building blocks of any digital communication system that you take. It could be a cell phone, it could be your laptop which is communicating over Wi-Fi or Ethernet. It could be satellite phones. Yes.
Modulator, what is the payment definition? What is it?
Okay, so for example, if let's take Wi-Fi. Right? If you noticed, typically the Wi-Fi bands which are used in practice, they're either 2.5 gigahertz or 5 gigahertz. Right? So if you bought a router or something recently, then you have seen that you have these options. But basically the data that you're trying to transmit has to be sent across these bands. So typically what happens is that each user is given a certain band around 2.5 gigahertz. So you can communicate only over certain frequencies. You have digital data, but what you're actually transmitting are sine waves. Right? So there's some mechanism, some way to convert this digital data, so sequence of bits, to convert them into a series of sine waves and then send them across an antenna. Right? So that's again, very loosely speaking, that is what I mean by modulation. Right? So essentially, modulation is basically a process by which you convert your data into a form which can be sent across the channel. That's one way to think about it. But there's a whole lot which goes on inside this particular block. Any other questions? All right, so this is one typical example of where you need channel encoding. Right, and in fact, we'll sort of set up the problem in general for these specific kinds of application, for communication applications. But that's not all where this can be used. So error correcting codes are also used in distributed storage systems. So what is the problem there? Let's say that you have an enormous database. So I mean, most of our data is today stored on the cloud, right? It will be stored on servers in Google or Facebook or whatever. And the total amount of data amounts to several petabytes or exabytes. Right? It's not like small terabyte kind of data that they have. So there's no way of keeping them all in a single disk. So what you do is you typically you have your entire database. It is split into chunks and then stored across several servers or several disks, right? So you typically split this and then store them on chunks. So in fact, even you use some kind of storage device of your own, like a NAS box, that is what you do. You have several, say, hard disks, and you have more data that you can possibly store in one particular hard disk. You may want to just split it across several disks. Now the problem with now, for example, if you are Google or Facebook, what is very important is that you never lose the data, and that data is available at all times, right? But then if you look at typical hard disks, they are quite unreliable. So typically, even servers, some servers are always down for maintenance. Some disks may fail, and at any cost, you don't want to lose this data, and you want to make sure that all the data is available at all times. So what do? So one way, of course, is plain replication. So you have some amount of data, you split it, you basically make another copy of it and then store it. So it's 2x redundant. So it's basically, but the problem with this is that you're taking twice the space. So if you have 1 petabyte of data, then you need disks worth 2 petabytes, right? Which is not good. And also, if let's say that, particularly if you're distributing it, let's say that each, again, as a toy example, if each disk can store up to 10 TB, and maybe you have 100 TB of data, then you will store it across 100 disks. Sorry, you'll store it across 10 disks. And if you want to replicate this, then you will store it in 20 disks. So basically, you have a copy of each disk available over here. Now, what can happen? Now, let's say that this disk and this disk fails. Then what do? You lost everything. So these are things that you definitely want to avoid. You should not lose any data. And these disks are always prone to failure. So how do can you sort of store this in a more clever fashion, so that even if maybe a certain number, of course, if all disks fail or if a certain number of disks fail, then you can't do anything. You will lose it. You will lose data anyhow. There's no 100% foolproof way of storing everything. But typically, you know roughly how many disks or how many servers are going to be online and how many of them fail at a particular time. It's typically around 5 to 6% of the servers are generally down most of the time for maintenance or other reasons. So given this particular information, how do you sort of carefully use? You don't want too much redundancy. Of course, you can always do 10x, right? You can replicate it 10 times, and you're sure that you'll always have something or the other at your disposal. But that's not an efficient way of doing it. So that is why people use error correcting codes to sort of make sure the redundancy is not too much. But at the same time, if only a certain number of disks fail, then you can still recover all the data. So we'll see some versions of error correcting codes which are used in practice, called Reed-Solomon codes. So these are used in storage systems today. Recently, there has been a lot of work in designing improved codes for distributed storage systems. But for example, if you heard of RAID, redundant array of disks, so RAID, there are different levels or different versions of RAID that you can use: RAID 0, 1, 2, 3, and so on. So 0 is typically there's no redundancy at all. I think 1 is simply means that it is replicated. I think RAID 2 uses some very preliminary code where basically in one disk you store basically if you have two disks worth of data, then in the third disk you store maybe the XOR of the first, what is the contents of the first two disks, the sum of the contents of the first two disks, that if one disk fails, then you can always recover from the other two. And there are more advanced versions of RAID which use what are called Reed-Solomon code. Basic versions of Reed-Solomon or BCH code. Yes. Huh?
I have only one.
Okay.
Want to build a 20% redundancy, maybe 1.2x.
Okay.
What is the factor that is coming from the other side? It's like partial recovery, like this.
So,
I can do it in 1.1x, 1.2x, complete.
yes.
Like that. Factor that is the other side. Whether it is full recovery, partial recovery, that factor comes.
So there are two kinds of parameters that we will look at. One is, of course, I mean, I'll describe this in a little more detail, but just to give a quick peek. So one thing that we're interested in, of course, is the redundancy. Right? How much additional space do we require in order to give some level of error tolerance? The second aspect that we look at is what kind of errors can this handle? So in the context of distributed storage, we say that, for example, I have 100 TB worth of data and each disk can store maybe 10 TB, and I'm willing to have maybe 1.5x space, so a total of 150 TB worth of disks. Then what is the maximum number of disk failures that I can handle? That is what we will typically be interested. But at all times, we want to be able to recover all the data. As long as the number of disk failures is less than a certain amount, we should be able to recover all the data. If the number of disk failures is more, then we don't care. We assume that everything is lost. So that's the kind of flavor that we will have in this particular course. But the point that you bring up is certainly valid. There are applications, particularly in communication, where it's okay if maybe a small fraction of the data is lost. So, for example, voice communication, right? So in voice, it's okay if maybe you lose a few milliseconds worth of information. You can still make out what is going on. But on the other hand, if let's say you're transmitting an image that requires certainly more, so for example, if you send an image to someone over the internet or over WhatsApp, you'll see that you always get back the original image, right? It's not cropped out in some part or blurred or anything of that. But when you're talking over the phone, it frequently happens that you lose some part of what the other person is saying. So depending on what kind of communication, what kind of storage you have, your error tolerance could change, right? And your code design will depend on what your error tolerance is. Yes.
So we need to keep a distance. When we know it's going to be, we know the idea, it can just migrate it.
Yeah, but then you have to keep migrating all the time, right? Some disks fail. Yeah, you don't know when it fails. Right?
Can do migrations at the probability case, right?
Yeah, but ultimately you will still, so let's say that you migrate, right? You will need extra disks, don't you? So that's redundancy.
Not us.
It depends. So if you know that it is going to fail, then you can migrate. But disks fail, so you don't know when they're going to fail. And you don't know which ones are going to fail. So and migration also involves communication. That is also an expensive. So there are various factors which come into it. But then again, if particularly if all you're interested is say server downtime when the server is going to be maintained, then you can always migrate it somewhere else. That's certainly an option. But these are mainly to handle scenarios where either you don't want to do migration every single time, or again you don't know that so it's some kind of a failure. Any other questions? All right. So here's another example that you would have seen every day: barcodes or QR codes. So if you noticed, a barcode, even if it's a little smudged, or even if part of a QR code is smudged, you can still get back the original thing. So let's do an experiment. So I have this QR code over here. You can take out your phone and see what this is. But before that, I'll maybe scratch out a little part of it. Okay, I'm going to just maybe erase some part. Okay, so it's smudged out. It shouldn't really matter. You should still be able to get it. Yeah. Right? So even if a part of it is smudged, of course, if there's a lot of it smudged out, then there's nothing you can do. But this does provide, yeah, it just goes to my homepage. So it does provide a fair amount of error resilience, right? So part of it is smudged out. Now I could also maybe, yeah, scratch in black. You'll still get it. So even this uses some form of Reed-Solomon error correction. So sorry? Oh, it's not working now? Now, is it? It's not? It is working.
So the concept is redundancy.
Yeah, there is some redundancy involved, but that essentially this also you'll see the codes that are used in QR codes as well. So these are what are called Reed-Solomon codes, which are used in storage and also in QR codes and many other applications. So also, I mean, other examples are CDs, DVDs, and Blu-ray discs. So even if you scratch a CD, I mean, just one scratch maybe, you can still get back the content, the content that was there. But eventually, of course, you lose information once it gets worn off or there are too many scratches. So all of these involve some form of error correction, but the kind of error correcting code that you design for each case could be different. The kind of error correcting codes that you use for CDs, DVDs, and Blu-ray discs could be different from the kind of codes that you use for, say, QR codes. But there's also a certain sort of, so we'll study it in such a generic framework that the kind of codes that you develop for one application could be used for other applications as well. So for example, I said Reed-Solomon codes. So Reed-Solomon codes are used in QR codes. They're also used in distributed storage. So it's the same code but different applications. But the kind of codes that are used in communication are different. And we'll see why that is the case, because your requirements are actually going to be different. Yes, yes.
QR code. So of that QR code,
Yep.
I'm using.
Okay.
Then going to the location where redundancy.
It's harder, yeah. It's a 2D format, right? So it's a bit complicated. But there is
Can I say that?
a very specific format.
Left rock.
There is something like that. I don't know enough, but you can look it up. There it is. So the QR code is very structured. There's a part of it which contains information. There's a part of it which contains redundancy, and so on. It's a fixed structure. So the format is fixed. Right? But depending on what you want to encode using the QR code, the kind of pixels that you have are going to be different. So in particular, I think the middle part is kind of does not contain too much information. You would have seen some QR codes with pictures in between. Get back to this one. Yeah, so it's not the kind of information is not uniformly distributed across the QR code. There are some parts which are more important and some little less. But again, that's the basic principle. Okay, so these were problems where you wanted some kind of error tolerance, right? There's some noise that is introduced or some errors that are introduced, loosely speaking, and you want to get back the data, recover data which was corrupted in some sense. But there are other applications which require no error correction, but at the same time error correcting codes are used. So here's an example. It's a classical computer science example of secret sharing. So you have a sensitive file, okay? That I call a secret, and I have a number of places where I can store this. I have a Google account, I have a Dropbox account, I have a USB with me, and I also have a laptop. But then I know that I can get hacked at any time. It is some kind of really private information. Maybe I'm a journalist and I have some secret information. and I don't trust any of them individually. So my USB could be stolen, my laptop could be hacked, my Google and Dropbox accounts could also be hacked. But at the same time, I know that I mean, the kind of parties who would want to hack me are not all powerful. They can't hack all of them. Okay, so maybe one of these could be hacked, but not all of them. So, for example, my Google and Dropbox account could be hacked, but then my USB is always going to be with me in person, and I also have my laptop in person. So I know that maybe that will be reasonably secure. Okay, so it's okay if maybe one or two of them gets hacked. I should still be able to protect my sensitive information, but at the same time, I should be able to recover the sensitive file that I have. So the secret sharing problem is the following. You have a sensitive file called the secret. Let's denote it S. I want to somehow store this secret in the following way. So it's going to be split into multiple parts. It's going to be somehow encoded in some fashion. Maybe I'll call it C1, C2, C3, and C4. And this should be done in a way that satisfies the following requirements. So the first thing is, if the first requirement is that S can be recovered from maybe any three of C1, C2, C3, C4. So if I have access to maybe Google Dropbox and my USB, I can recover S. If I have access to Google, my USB and my laptop, then I can recover the original secret file. But if I have access to any fewer than this, let's say I have access to any two of them, maybe only Google and Dropbox or only USB and laptop, then I should be able to get absolutely no information about S. What I see is complete garbage, and I can make no sense of it whatsoever. So this is a classic problem called secret sharing. And it turns out you can use error correcting codes to design good secret sharing schemes. At least for certain kinds of secret sharing problems, the certain even Reed-Solomon codes are essentially. So I've been repeating Reed-Solomon codes for 2 to 3 different applications. So you can see that it's a great code. Right? So that's a problem which has nothing to do with communication, but still is an application where error correcting codes are used in practice. Yes.
While sharing files are there, encryption plays a major role and better role than why there is important.
So this is, in principle, this is also a problem of cryptography. And there are many crypto systems which are based on error correcting codes as well. So this is again one problem which is studied extensively in cryptography, the secret sharing. So typically, if you look at whatever public key or private key cryptography, it's a slightly different problem where you want to communicate something, and you have some sort of a key with you. So here you are assuming that in this particular secret sharing problem, there's no assumption that you have an extra key or anything of that sort. So in particular, this is also applicable to other kinds of problems, wherein, for example, things like bidding and so on. Well, bidding is maybe not a good example, but basically you have multiple parties, okay, and you want to share a secret with multiple parties, but they're not trustworthy. You know that some of them can be malicious, but at the same time you want to ensure that as long as a certain number of people get together, they can get back the secret. But if fewer than those many people get together, then you should not get to know what the secret. It's a problem of that. Yeah. Any other questions? Yes.
Greatest trustworthiness. Just think that two and below that we can't.
Correct.
So greatest cheating and.
Yeah. So basically we're assuming that no more than two people are malicious. That's an assumption that you will have to make. So there's an upper bound on how many malicious. That's a problem that is typically comes in any sort of multi-party cryptography kind of a problem. There's an upper bound on how many malicious parties there are, or the power of the adversary. And as long as it is less than that, then you want to be secure. But any more than that, there's nothing you can do. Okay, so here's another maybe sort of a puzzle for you. So this is broadly called the group testing problem. Okay. So let's say that I have 7 people, okay, and they could potentially be infected with the disease. Okay. For example, the coronavirus. Right? But you know that at most one person, you know the statistics of how many people in general could be infected and so on, and you know that maybe out of these 7 people, either no one is infected or at most one person is infected. Okay. So that's fine, and you want to know who the infected person is. You want to immediately quarantine this person. But the problem is I have only 3 testing kits. Okay. That's a problem that we have faced in the last few years. So you have 7 people, 3 testing kits. If you had enough testing kits, of course, you could just test each and every person and be done with it. But now I have only 3 testing kits. I know at most one person is infected. So now what do I do? So what you can do is you can pool together samples. So for example, you can take swabs from all of the 7 people, but instead of testing each particular swab, you can take the tissue samples, you can combine tissue samples together and then test. So basically, let's call these, give these people names. So let's P1, P2 up to 7 people. Okay. Now I can pool tests. So for example, I can pool P1, P2, P3. If I take the samples of P1, P2, P3 together, and then I use just one test on this pool, then if any one of P1, P2 or P3 is infected, then it returns a positive. Now I don't know which of P1, P2, P3 is positive, but I know that one of them is positive. If it's a negative, then I know that all of them are safe. None of them are infected. Okay. So that's the setup. Okay. And now the puzzle I'm giving you is, now I have 3 testing kits. How do I find out who is infected? I claim that 3 testing kits are enough. Okay.
If we have in log of n.
Okay, but give me a scheme.
4, 3.
Fine. So the scheme that you are proposing is that I'll pool together. So my first test would be, I pool whatever P1, P2, P3, P4, okay, and I test them first. So if it returns positive, so if it is positive, then I know that one of these 4 guys is infected. If it is negative, then either no one is infected or one of the other 3 guys are infected. Okay. So now let's say, so if it is negative, then what do you do?
We test the other.
Do you want to test the other 3?
Okay.
So we can test 2 of them. Right? So let's say that I test P5 and P6, Okay. I know that now if one of them is infected, so now this could return a positive or a negative. If it is positive, then maybe I test only P5. So if this returns positive, then let me put this in brackets, meaning that this. So P5 is positive. So I know that the fifth person is positive. If it returns negative, then I know that the sixth person is positive. If this test, if P5 P6 was negative, then I just test P7. If it is positive, then then I know that P7 is this, or otherwise no one. Right? So now I test P1. So if this first test was positive, then I know that at least one of these guys is positive. So then I can test maybe P1 and P2, the first two people. If this test turns positive, then I test maybe P1. If it is positive, then P1, otherwise P2, and so on. Right? So this works. So you can get to know, just using 3 tests, you can find out which of them is infected. Now, this is what is called an adaptive scheme. So basically, the next test that you do depends on the result of the previous test. So depending on whether the first test gave you a positive or a negative result, you decided to test P1, P2 or P5, P6. Right? So now let's take the RT-PCR kind of a setup where it takes a certain amount of time. Right? It takes time to get back the test result. And I don't have the liberty of waiting for the test to decide whom to test next and so on. Right? Because then whatever it takes, maybe 10 hours, it takes 10 hours to get the output of my first RT-PCR test. I have to wait for 10 hours, then decide who to test next and so on. And time could be of the essence. So is there a non-adaptive scheme of finding out, just using 3 tests, finding out who the infected person is? So do you get the problem? So basically, I have 3 tests. Who I am going to pool for each of these tests has to be fixed first. I test all, I do those tests simultaneously, and then then whatever, wait for the results, and immediately I can't do any more tests. Yeah.
So first 4, like basically finite number.
Okay.
4, 3, the first 4, alternating 2, alternating 1 together, like.
Okay, so let me perhaps try to write this down. So I have 3 tests, right? T1, T2, T3. Maybe.
So now I have.
Okay, so let me just write a 1 if that particular person is going to be tested in that particular test or not. So what is your what?
1, 1, 1.
Okay, so the first test is going to test the first and not test the last 3 people. Okay, and then
1, 1, 0, 0.
1, 1, 0, 0, 1, 1. Okay,
1, 0.
1, 0. So okay, so now this is the way you're going to test. So test 1, you're going to pool the first 4 people. For test 2, you're going to pool P1, P2, and then P5, P6. For test 3, you're going to pool P1, P3, P5, and P7. Okay? And now is it clear why this works? Is it clear to everyone why this works? So let us say that say person 1 was positive. Okay, then what would be the output of the 3 tests? Positive, positive, positive. Now let's look at the columns of this particular array that I have written. right? So all of these arrays are kind of distinct, right? None of them repeat. So if person 1 is positive, then I'm going to get positive, positive, positive. If patient 4 is positive, is actually infected, then I'm going to get positive, negative, negative. And if anyone else is infected, then I'm never going to get this particular result, positive, negative, negative. Okay? So that is why this works. So you should convince yourself that this works. If no one is positive, then you'll get negative, 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 and you know that no one is infected. Correct? So this is a scheme for what I call non-adaptive group testing, and it turns out that this particular matrix that I've written over here is essentially a matrix connected to what is called the Hamming code. So we'll see this in a few classes later. This, in some sense, describes the Hamming code. The 7, again, I'm just using this notation, what is called the 743 Hamming code.
Do you know this before or you came up just now?
But did you know the connection?
No, I.
Alright, so that's sort of the connection. I mean, although there doesn't seem to be any obvious connection between the two, it turns out that, I mean, if possible, if you can remind me or if I remember, I'll sort of point out the connection as to why an error correcting code can be used for group testing. Particularly if there's only one patient, then effectively what this we'll see that there's a very simple connection to between communication in the presence of errors and the problem of group testing. Right? So once you see error correcting codes, this connection will be more obvious, but at this point maybe it is not. So this is basically what I have. Again, depends on the order in which you do it, but this is one way to write the parity check matrix of Hamming code. Okay. Now, there are many other applications. Maybe I don't want to spend too much time going over all of these. So, in fact, so in recent years, there has been a search for good cryptographic schemes which are resilient to quantum attacks. Right. So right now, there's a huge amount of development in designing quantum computers, and many of the classical crypto systems like RSA could potentially be vulnerable to quantum attacks. So in general, so the way you construct a crypto system is the following. So the general idea is that you have a message that you want to keep secret and you encrypt it in some fashion. Or you want to be able to recover the original message as long as you have a certain key. If you don't have the key, then you should not be able to recover. But does that mean it is impossible to recover without the key? No, it is not. But the general idea in most crypto systems is that it is computationally very hard to get back the message or the secret given only the encrypted version. Right? So from the encrypted version, in principle, it is possible to get back the secret. But it is computationally very hard to do so. So for example, you could sort of search through the entire message space to find a match, and that could work, but that's going to take you several years. So these are all based on sort of reductions to hard mathematical problems. So one hard mathematical problem based on which crypto systems are designed is the problem of integer factorization. If I give you a very large number, which is then how easy is it to factorize it as a product of primes? It turns out that this is a hard problem. But this is a hard problem for classical computers. But on the other hand, if you have a quantum computer, it turns out that there's a polynomial time algorithm to do integer factorization efficiently. I mean, we are far away from designing quantum computers which can do prime factorization. So all your passwords are currently secure, but of course they're still vulnerable to brute force. No, the algorithm. So it's theoretically proved that it is polynomial time, right? But still, so you don't have an efficient, really efficient algorithm to do it. But since it is polynomial time, it can always be improved upon. And the second, you don't have quantum computers which can currently even match what classical computers can do. So even the best quantum computers today can only maybe multiply small numbers. That's it. But of course, that doesn't rule out the possibility of being able to construct better computers. So the main problem is then to design better cryptographic schemes which are based on even harder problems. So prime factorization, it turned out, was very hard to do using classical computers, but fairly easy to do using quantum computers. But there are other problems, mathematical problems, which are hard to do both by classical computers and quantum computers. And it turns out that one problem which is hard to do by both, or conjectured hard to do by both, is decoding a random error correcting code. So if I give you an arbitrary huge error correcting code and I ask you to decode it, it turns out this is a computationally very hard problem. Right? And this has been used to design what are called post-quantum cryptographic schemes. And so there's been a lot of work in what are called lattice-based cryptosystems, and based on the similar ideas, cryptosystems based on error correcting codes. These two are very intimately connected to each other. So the very high level basic idea is that if I give you a random code, then decoding this over a noisy channel is going to be very, very hard, computationally hard problem. But then there are specific codes which can be decoded very efficiently. Okay? So the high level idea is to use the key. So for example, I somehow convert my code into some other code, so that if I have the key, I somehow get back. The problem essentially amounts to decoding the easy code, but for an attacker, since he does not have the key, his problem of recovering the message amounts to decoding from a random code, which is hard. So again, if you're interested, you can look it up. There are what are called Michaelis cryptosystems and so on. If you just look at post-quantum cryptosystems based on ECCs, then you'll get a whole bunch of different sources. So again, there are many other such applications of error correcting codes beyond just communication. Designing hash functions like the SHA hash functions, if you've seen it before, and then compressed sensing and so on. So we'll only be able to scratch the surface of the field of error correcting codes, but the goal of this course is to at least give you a flavor of what is known and what kinds of tools and techniques are used. So this course is essentially, in some sense, philosophically, it's going to be split into two parts. So initially, as I mentioned, we'll mainly be dealing with algebraic and combinatorial techniques for designing error correcting codes. And these work well for certain kinds of applications. But none of these are actually what are used in, say, our wireless communication system. They're used in some parts of wireless communication systems, but these are not good for wireless communication. But they do extremely well for problems such as storage and cryptography and so on. In the second half, we'll see a different kind of codes, turbo codes, convolutional codes, LDPC codes, and so on, which don't work very well they can work well in certain scenarios, but mostly they're mainly designed for problems of communication. And we'll see why these two are different. And the way the fundamental ideas in designing these codes, in designing algorithms to encode and decode, are going to be very, very different. Right? Okay. So let's get down to the actual problem of what is error correction. So here's the basic model that we will use for the rest of this course. So we have something, what we call a message. Okay, it's typically going to be a k-bit sequence. Okay, so sometimes I'll say that this is going to be k-bits, or sometimes in principle this alphabet from which the messages come from is not terribly important, because for us there are going to be one of a certain number of messages. I could say that the message could be a k-bit message, so it means that there are 2 to the k possible different messages. Or sometimes I will just say that the message comes from some set of size maybe m. So it's one of m different messages. So for example, this could be one of m different images that I want to transmit, or maybe I have one of m different words or sentences that I want to transmit. For example, in let's say old telegraph, there were certain messages that you could send, and that's it. You can't send anything. There are certain fixed messages that you could send from one person to another. So there's a certain set of messages that you can send, and that is going to be fixed beforehand. And or it's going to be a sequence of k bits, and the assumption is that we know what k is. Right? The goal is to and the goal is to somehow send this across a noisy medium, or something which can cause errors, and that is what we will denote as the channel. So this errors or introduces what I generically call noise. So this noise could be different from what you think about when you think about noise, but in general it's an unreliable system over which I want to store something or I want to transmit something. So the goal is to convert this k-bit message into an n-bit sequence or n-symbol sequence. So this is what I'll call a code word. You convert your k-bit message into maybe an n-bit code word. That's what I call the process of encoding, and this is sent across the channel, and at the output of the channel you receive some n-bit or n-symbol sequence, and the goal is to get back the original message as reliably as possible. In certain applications you will want these two to be exactly the same, but in certain applications you're okay if they're different with a small probability. You want to make sure that the probability of error is as small as possible, or it's exactly the same. But in all of these problems, we assume that some description of the channel is known to us. So either the statistics of the channel are known. So in channel coding, you would have seen discrete memoryless channels, or it could be that you have a certain error tolerance level. So for example, in the problem of storage, no more than 5 disks out of 100 disks can fail. So the channel could cause failures for at most 5 disks, no more than 5 disks, but there's no definite pattern as to which 5 disks could be in error. And the kind of errors that I'm saying, they could be kind of different. But in all of these, we're obviously interested in A, the kind of error tolerance and reliability that we can guarantee, and B, how much additional redundancy that we have to introduce into the system. So the redundancy is going to be measured using this quantity called the rate, which is how much additional overhead you have to put in. Right? So I have k-bit message, but I'm going to convert it into a code word of length n. Right? So I'll assume that each code word comes from some alphabet f. It could be a sequence of bits, but in general it could be a sequence of some other symbols. So I'll generally assume that each xi comes from some f, and each message symbol comes from some set calculated m. And again, there's a little bit of difference in how the rate is defined from one reference to another. So some books define the rate as log of the number of possible messages divided by log of the number of possible code words that are possible. Also, some of them just use 1 over n times log of the message space. Okay. So I'll explicitly say which definition I'm going to use, because again, different references are going to use different definitions. So don't be confused. Right, so that's the basic model that we'll follow. So let's look at each of these blocks one by one. So let's look at the channel. Right. Now the channel, depending on what kind of a problem you have, what kind of an application you have, the channel could behave differently. So one class of channels are random noise channels. So these are channels where essentially there is some stochasticity in the medium, for example, a wireless channel, and basically there's no malicious party involved. So symbols could be independently corrupted, right? Randomly and independently corrupted. So one simple example is the binary symmetric channel. So what is this? You send a sequence of bits. Each bit gets independently flipped with a certain probability p. So I transmit 0 1 0 1 1. So basically for each bit you toss a coin. So with probability p, you flip this from 0 to 1. With probability 1 minus p, you leave it as it is. So right, so you transmit a bit sequence, you receive another bit sequence, and each bit is independently flipped with probability p. Has anyone not seen the binary symmetric channel before? Okay. Another simple example is the binary erasure channel, wherein it's similar, each bit is independently corrupted, but now the corruption is kind of different. So bits are never flipped, but they could be erased. Right? So for example, think of it as with a certain probability p, you decide to kind of completely smudge what has been written. So you know that something was written over there, but you don't know what it was. So that's the binary erasure channel. So at the transmitter, you can send a sequence of bits, where the receiver, you can get either a 0 or a 1 or a special symbol, which I call the erasure symbol. And I denote that by E. So that's the binary erasure channel. And these are both examples of random noise channels. Now, yep.
Why do we need an erasure? Like, if we know that something was missing, can't we just simply replace it by one of the places and then proceed?
So basically, that's suboptimal. You don't know which one it was, right?
Yeah. So like we can then analyze it in a different way. So why need for this particular?
Oh, because that what you're mentioning. So basically, what you're saying is, if I receive an erasure, basically I don't receive anything, then I just replace it by a random bit, 0 or 1. That's what you're suggesting, right? It turns out that's extremely suboptimal. Okay, so now you've taken the information theory course. So suppose that I did that. Okay, then what would happen? So that's equivalent to some other channel, right? So basically, what you're saying is I transmit either 0 or 1. With probability 1 minus p, I get a 0. With probability 1 minus p, if I transmit a 1, I get a 1. Okay. Now, if I receive an erasure, what do? I randomly replace it with either a 0 or 1 with probability half.
So we can just map it to one of the fixed symbols, and we can always make it that there is an erasure, we always read it as 0.
Oh, you always read it as 0. Okay. So let's say that, so basically what happens is with probability, so it's equivalent to the following channel, where if you transmit a 0, you always get a 0. Right? It could be erased. Even if it is erased, it becomes a 0. If it is a 1, then it gets erased, then you basically get a 0. Right? So this is the Z channel. Okay, what is the capacity of this channel? It's going to be less than the capacity of the binary erasure channel. And one simple reason why this is not optimal is because you're doing some kind of post-processing, right? And from the data processing inequality, you know that if you do some kind of post-processing or pre-processing, then the capacity can only reduce. And it turns out that if you do any such kinds of post-processing, capacity will strictly reduce. So, in fact, the binary erasure channel is kind of nice. It's one of the best kinds of channels in a certain sense. And the binary symmetric channel, so you gave the other suggestion, right? If I get an erasure, then I randomly just replace it with either a 0 or 1 with equal probability. So if you think about it a little, that's equivalent to a binary symmetric channel. And it turns out that's the kind of the worst post-processing you can do, because that will give you the least capacity. All right. Any other questions? Okay, so these are sort of what I call random channels. But then in applications such as storage, you will want to see certain different kinds of models, wherein channels are not completely random. So what can happen in a random channel? So one, the noise is completely arbitrary in the sense that, okay, there's a certain structure to it, but there's a certain probability that everything it is received exactly as it was transmitted. And there's a certain probability, however small, that things go horribly wrong. Right? So for example, if you transmit, say, 10 bits across a binary erasure channel, then it's a small probability, but there's a non-zero probability that you get all erasures. Right? But then over such a channel, typically, if you look at a long enough sequence, the number of erasures you're going to see is going to be roughly n times p, because you're erasing a symbol with probability p. It's kind of, think of it as tossing a coin with probability of head being p. If I toss, say, 100 coins, 100 such coins, how many heads would I expect to see? Roughly 100 times p, right? And the same thing happens here. Because noise is completely independent across bits, you would expect to see roughly n times p erasures. Not more than that, not too much more than that, not too much less than that. So that's a very nice property of random noise channels, that there's a certain typical behavior that you can associate with these channels, right? But in many other situations, you don't care if the number of erasures is more than a certain amount. There's nothing you can do anyhow. But you want to take care of but as long as the number of, let's say, errors or erasures is less than a certain amount, you should be able to correct it exactly. You should be able to recover exactly what was transmitted with no error, as long as the number of errors is less than a certain threshold. And this should happen even if the noise is added adversarially. So, for example, think about the following problem, where, let's say, you write down on a piece of paper. Okay, you somehow design an error correcting code. So you have a message, let's say 01101. This is your message, and then you convert this into a code word, and maybe you write it down on a piece of paper. Now, someone who's now think of the problem as though there is an adversary who can maybe replace 3 of these bits. He can replace any 3 of these bits, and he can see these and replace which 3 he wants to. The only constraint is that whatever the number of locations which he can manipulate is fixed, only the number. But beyond that, he is free to choose which locations to replace and how to replace it. So that is what is called an adversarial bit flip channel. There is an adversary who can replace any NP locations with whatever he wants. So in particular, he can flip at most NP locations, and he can do it after seeing the entire code word. That's a very powerful adversary. Right? So this is, this may seem similar to the BSC, because in both cases the number of errors you would expect to see is roughly n times p. But it turns out that this is strictly worse than the other, because in the random noise channel, the noise is added independent of which code word is transmitted. But in this case, for every specific code word you transmit, you can tailor one particular attack, the worst attack, right, by choosing exactly which bits to flip. And it turns out that that makes a big difference. In fact, we'll see both of these cases. What is a maximum rate at which you can transmit across an adversarial channel versus a random noise channel, and it will turn out that this is far lower than what we can do over a random noise channel. Okay? So one other way of thinking about these bit flip channels, the BSC or the adversarial bit flip channels, is the following way. It's kind of an additive channel. So basically there are n transmissions, you transmit n bits. So you have n transmissions. The received symbol, the received bit, the ith received bit can be thought of as the ith transmitted bit XORed with an error bit. Alright. So if you think about the XOR operation, if Zi is equal to 1, then what is Yi equal to? Is the complement, right? So basically there's a bit flip. So there's a flip if Zi is equal to 1, and if Zi equal to 0, then Yi is equal to X. So another way of representing these bit flip channels is as a modulo 2 or an XOR additive channel. All right, and we'll make use of this this particular fact. Right? And similarly, if you think about it, the BSC can also be thought of in the same way. So it is Yi equal to Xi plus Zi, but now instead of Zi being sort of adversarially chosen, Zi is going to be a random Bernoulli P random variable. For the BSC, in which case Zi or IID Bernoulli P random variable. Right? The same holds for the erasure channel as well. So in a random BEC, basically each bit is erased independently with a certain probability, irrespective of what was transmitted. But in an adversarial channel, basically you transmit a sequence of bits. There's an adversary who sees exactly what you wrote down, and then he decides to erase at most whatever NP locations. There are at most NP erasures, and he can choose to erase whichever ones he wants. So there is this difference between random noise and adversarial noise channels, and in general, adversarial noise channels are very, very hard to handle. In fact, we don't even know what is the optimal rate of transmission for most adversarial noise channels. Okay, so maybe let's stop here. It's 3:55. Yeah. Sorry?
Example of adversarial.
So this is an example of an adversarial noise channel.
In real life.
Oh, in real life, you can think of it as though, so one other problem is sort of think about a jammer, right? So you're transmitting something, right? And then there's a jammer who's maliciously trying to add noise. So and it's not just, I mean, typically when we think of jammers, we think of just adding random noise with sufficiently high power. But there are cleverer things that you can do. If you know that you're using a specific protocol, you can design specialized ways of jamming techniques. And handling those are harder than handling random noise. Okay. Any other questions?